Okay, we're now moving on to our last section, which is going to cover the segment routing innovations for multicast in iOS XR 7.3.1. There are many innovations on multicast in this release. We're going to be covering primarily the availability of dynamic segment routing point-to-multipoint policies. We will explain what they are for and how they are set up. Dynamic segment routing point-to-multipoint policies. They are new in iOS XR 7.3.1. What they allow is the delivery of multicast services over a segment routing domain. They're used to build multipoint trees that represent provider tunnels that are instantiated using these segment routing point-to-multipoint policies that are computed by a PCE. The mechanisms that are used to discover the endpoints of a point-to-multipoint policy, as well as to signal the customer multicast flow mapping and signaling, is done via well-known mechanisms from BGP multicast VPNs. The main use case for this dynamic segment routing point-to-multipoint policies is the creation of BGP-based multicast VPNs, with the added benefit of not having any state in the core of the network. So if we look at the illustration, we have a segment routing MPLS network with a root and leaf devices, also a segment routing PCE, which is going to compute a point-to-multipoint path. A segment routing policy will be instantiated into the routers in the network, in this case A, B, C, D, and E, and the corresponding forwarding state will be installed such that multicast traffic can come down at the root node and then be replicated efficiently in the rest of the network in its way to the receivers. The MPLS label that we see in green in this drawing that is used for the replication and the encapsulation of the multicast traffic is what we refer as the tree segment identifier, or tree SID. But if we go in a little bit more details on how these policies work, we have the following highlights. If we look at a segment routing point-to-multipoint policy, it is a augmentation of the well-known segment routing point-to-point policies that you likely know by now. The identifier of a point-to-multipoint policy is a root node, in this case, the root node being node A, and a identifier, for example, a tree identifier of X. As an attribute of the policy, we will find the leaf nodes, in this case node D and E, the tree SID label, the MPLS label that represents the tree. In this example, let's use the value 15,000, and then the actual path. The actual path will tell me where are the replication points in the network. So when the traffic gets on A, I replicate that on interface 0. When it gets to B, I replicate on interface 0 and interface 1. When it gets to C, it replicates on interface 0. When it gets to the leaves, there is no further replication. The packet is decapsulated and sent to the proper receivers. So as you can see, it will allow the efficient delivery of multicast VPN traffic. You will learn in a moment how the endpoints and the customer multicast flow and state is signaled with well-known BGP. You will learn also how the policy is computed by the PCE and signaled by the PCE to the network elements using PSET. And you will also learn about the presence of the different type of nodes. Obviously, on a tree, you can have a node next to the source of the traffic, your root node, you have the leaf node, but in between you have your pure replication nodes, or what is called as the bud node, a node that replicates as well as is acting as leaf for local receivers. As you would expect, the type of core trees that are supported are the ones that are well known in multicast, such as the default multicast distribution tree, partition multicast distribution tree, and optimized data multicast distribution trees. We're going to describe a little bit more the reference architecture that includes the dynamic segment routing point-to-multipoint policies. And there are three key elements. One is your orchestrator. In this case, we're going to describe the orchestrator function being done by Cisco's NSO. You have a path computation element, or the segment routing PCE from Cisco. And then lastly, you have a segment routing MPLS network. The functions of the orchestrator will be primarily to be able to instantiate a VPN, a service, a multicast VPN. The idea here is to be able to program the PEs that are members of the VPN in an automated fashion, in this case from Cisco's NSO. The second element is the MPLS, the Segment Routing MPLS network, which will provide a segment routing enabled underlay. It would also include the ingress and egress PEs part of the VPN running BGP for MVPN, and therefore be able to discover the endpoints as well as the customer multicast information. And then on this same node is where you are going to be programming the tree. And for that, we're going to be programming the tree seed of the tree, leveraging the label switch multicast support that is on the data plane of the devices in the network. And lastly, we find the path computation element, or Cisco's SRPCE. This is the element or the function that will discover the topology either by being part of the IGP or via BGP link state, and it's going to be responsible for the computation of the path of a point-to-multipoint policy. The computation will be done in multiple criteria, such as the optimization objective, which is basically the metric type of the tree. Either it is the IGP metric or the TE metric or even the latency or the delay metric of the links in the network, and any available constraints, for example, affinity constraints that we would like to take into consideration when a point-to-multipoint path is being computed by the PCE. The PCE will also be responsible for the actual signaling of the policy down to the network elements, as we will see later in an upcoming sequence by leveraging the PCEP protocol. So in this sequence, I want to describe how the default MDT is created on PEs part of a multicast VPN. As you know, the default MDT will be rooted at every PE and includes all the other PEs in the network. We will describe how the signaling mechanisms of BGP for multicast VPN have been augmented to also support a new type of core tree, and that is the segment routing point-to-multipoint tree. So in the first step, we use the orchestrator NSO that is going to configure 3 PEs in the networks, node A, D, and E. The configuration of the service will be applied to the 3 PEs as you would expect. After being configured for a particular VPN, the presence of the configuration will make each router that is part of the VPN, in this case we're going to highlight router number A, to actually contact the PCE and trigger the creation of a new segment routing point-to-multipoint policy. This policy will be rooted at A, for example, and with a tree identifier of number 10. At this point, we're only triggering the creation of the new tree. The SRPCE will not have information yet on what the leaves are, but regardless, the tree is first created. As a result of being fully configured with BGP, the distributed control plane of BGP will make every PE, in this example A, of announcing what we call the BGP auto-discovery routes for MVPN. In particular, we talk about the route type 1, which is basically the inclusive PTME route. This route has been augmented to include a new tree core type, which is of type SR point-to-multipoint policy. This information regarding this new tree rooted at A and with the tree ID X is included into what is called the PTME tunnel attribute, or PTA. Likewise, the other PEs part of the network are going to be sending their corresponding type 1 routes for the VPN in question, so therefore router A is going to discover the other PEs that are part of the service. In this case, it will discover PED and PEE. The arrival of those routes from BGP is going to cause the router A is going to update the PCE, and it will provide the information regarding the leaves that have been discovered. So the tree that was previously triggered now is going to be augmented with the leaves of D and E. That becomes the first key information for the PCE to start to compute the point-to-multipoint path. With the information and the topology that it has of the network, the PCE is going to be able to compute the path. In this case, the path will be started at the root A with leaves D and E, using node B as a replication point in between on its way towards E. The tree seed will be assigned to the tree, and in the next step, the PCE will proceed to communicate with every router member of the tree to propagate the information. Information such as what is the MPLS label that is going to be programmed in the forwarding alongside the replication points that correspond to that label. So we can see via PCEP the communication going to nodes A, B, C, D, and E, with the corresponding replication points shown in the left-hand side. Lastly, each node is going to program its forwarding according to the information that came via the PCEP protocol. And now we are ready to pass traffic. It's important to highlight that the same procedure used to create the default MDT at router A will also happen at router D and E. Well, the control plane has already provided the information such that the PCE could compute a tree with dynamically learned leaves. The computed path was signaled down to the network elements. The network elements program the data plane, and now we can try to follow the data plane as multicast traffic arrives at the source, router A, and let's imagine we have receivers sitting on behind PED and PEE. The traffic will be replicated on interface 0 and interface 1 at A. We can see that the tree seed label has been used to encapsulate the multicast payload on the route. Furthermore, we can see that the replication points or the transit nodes, routers B and C, will simply exercise the forwarding entry associated with the tree seed label, 18,000 in this case. There is only replication to a single interface on B, that's interface 0, as well as single interface on node C, interface 0 towards node E. Lastly, the traffic will make it onto the leaves, router D and E. It will be decapsulated and forwarded to the proper interfaces where there are interested receivers. And that completes the sequence from that is going to be used to discover the VPN endpoints, propagate the information to the PCE so that it can compute the path for the newly learned leaves, and signaling an instantiation of the point-to-multipoint policy down to the network elements that ultimately will allow the forwarding of traffic. There are similar procedures that we're not showing for how a partition MDT and an optimized data MDT will be created. But it is the same knowledge that you already have from BGP Multicast VPN applied with a new core tree type of type SR point-to-multipoint trees or policies. Segment routing point-to-multipoint policies are standard technology. There are several drafts going on at the IETF where the tree seed itself as the building block of the segment routing point-to-multipoint policy is defined. Also, the architecture of a segment routing point-to-multipoint policy, the multicast VPN procedures, the PCEP extensions, as well as the Young model are all specified in IETF drafts. Okay, so we're going to jump into a few devices to show you a live demonstration of dynamic segment routing point-to-multipoint policies. So right now you're watching the console of the PCE. We're going to try to show you the different configuration elements and operational elements of the solution. So from the PCE, we're going to take a look at its configuration, which is going to be very minimal. In this case, the PCE is going to be configured with a point-to-multipoint configuration stanza, where we're going to tell the PCE what are the labels that it can use for tree seeds. In this case, the labels are from this range shown in here. This label range actually is going to grab labels from the so-called segment routing local block in each node. So the programming of the SR point-to-multipoint policy will leverage labels that are allocated from the SRLV of each node in the tree. As mentioned in the theoretical section, the PCE will actually maintain PCEP sessions with every element of the network. In this case, I have a topology that includes 5 routers, so the PCE will have 5 PCEP sessions. The PCEP sessions will be used to signal or to instantiate a point-to-multipoint policy on a router that is member of a tree, whether it is a root node, a leaf node, a bot node, or a plain replication node, transit node. So having shown you the PCE and how very little there is right now, we're going to go to the root node of my tree. So here I am in the root node. What I'm going to describe to you and show you is the configuration of 2 multicast VPNs. We're going to start with the first VPN that only has a default MDT, and at the end we're going to show you a second VPN that has default and data MDTs. So let's go with the simpler one, and let's look at the key new elements of the configuration. So under your multicast routing, you will configure the VRF. In this case, I'm calling it sample MVPN1. We're going to enable BGP VPN endpoint auto discovery using segment routing point-to-multipoint policies. We're going to also allow the creation of a default MDT, also using segment routing point-to-multipoint policies. Whenever the segment routing point-to-multipoint policy is going to be created, it's going to be associated with the information available on a segment routing traffic engineering on-demand next hop template of color 10,000. And this tree will also be asked to be computed by the PCE, including fast read route link protection. I'll explain that in a moment. But let's actually come back to this element of the color. So I'm sitting at the root, and I'm saying that the MDT default tree for this VPN is going to be associated with color 10,000. Well, when I go to segment routing traffic engineering, I have an on-demand color template for 10,000, and it's here where I'm going to specify what are my desired optimization objectives, i.e. what is the metric type that I want to optimize in the tree, and what are the affinities that I would like to include or exclude. In this example, I will not have any affinity constraints, and I will have a metric for this tree of type IGP. This configuration for the multicast routing for each VPN, as shown in the previous command, is going to be done on every PE in the network, root and the leaf nodes. But to highlight some of the differences of what needs to happen on the leaf, we're going to go to one of the egress PEs. So now sitting in the console of a leaf node, we're going to take a look at its PIM configuration. So for the VPN that we are configuring, the PIM configuration will include a reference of the RPF topology to a route policy. This route policy will allow me to specify the type of core tree that I want to use in my RPF topology. So here I'm specifying segment routing point-to-multipoint policies. Under PIM, I will also specify the use of customer multicast routing and state using BGP. So imagine, as it is the case here, I have my root and my leaf nodes configured as shown. Now we're going to come back to the root node and take a look at the operational data. So here we can see the multicast VPN routes present for the sample MVPN1. We can find 3 routes. 2 of them are route type 1s. These are the routes used for BGP auto discovery of the VPN endpoints. They are intra-AES IPMC routes. One originates at this router 1.1.1.1. The other one originates at my other PE number 4, with the loopback 1.1.1.4. These are the routes that are going to be used to discover the VPN endpoints, and that this PE is going to give to the PCE as a leaf in order to compute a point-to-multipoint path, including all the leaves that have been discovered. The other route type we see in the output is a type 7, which is a source join coming from PE number 4, and is asking for a join of a source-specific multicast with the group 232.0.0.1 and the source 3.3.3.1, which is reachable via the root node. Well, if we explore now into what we call the MVPN context data for the VPN that we are evaluating, we are going to focus here on the segment routing point-to-multipoint core tree data. And there are key parameters of information here. One is whether this sample, this VPN, MVPN, has a default MDT or a partition MDT. With the configuration I showed you earlier, we have a default MDT with the ID 524289. This is a very important number. This is one of the identifiers of the segment routing point-to-multipoint policy that I described earlier. The other identifier is the identity of the root itself. So 524289 is going to be a number that we're going to be reusing as we explore the trees that have been computed at the PCE. But before we go there, we want to take a look at what we call the MBPN database segment routing entries, where we're going to confirm that in fact we have discovered in the default MDT an IPMC leg, and the leg corresponds to the PE with the address 1.1.4, and the tree ID corresponding to the default MDT is again 524.289. You can see here that that default MDT was brought up using the requirements specified under the segment routing traffic engineering on-demand or ODN template for color 10,000 that we looked at the configuration at the beginning. Now with this number, 524.289 or the tree ID, we are going to go to the PCE and discover what has been computed. So let me just space out here. So now I'm going to ask the PCE to give me the details of the LSP of type point-to-multipoint that is rooted at 1.1.1.1, which is my root, with the tree ID that I pasted earlier, that I highlighted earlier. So let me actually hit the space bar. And here we can see that this is the information for my tree, rooted at 1.1.1 with the tree ID that I mentioned. This particular segment routing point-to-multipoint policy is going to have a tree-seed label of 15,562. This label was automatically allocated or determined by the PCE. This tree was computed to minimize the IGP metric. This tree was computed to provide local LFA FRR. Remember that my default MDT in the root was requesting local LFA FRR. And now when we look at the path, there are 3 nodes in the path. Node number 1, which is the root itself, is an ingress node. We can see how the tree-seed label value is going to be programmed at that node, and the outgoing replication point will be towards node number 3. So this is my outgoing label will be the same tree-seed label value, and my downstream node in the tree will be router 3. So now we go to router 3, which is now shown as node 0 in this sequence of nodes. Router number 3 will be a transit node. The incoming label for the tree will be again the same value, 15562. The outgoing label will be the same, and then the downstream node will be router number 4, 1.1.4. In this case, this is a leaf. And we can see here, node 2 represents 1.1.4, is my egress node, it is my leaf. There are no replication points on this node. So this is the computed path as being displayed by the PCE. Now, the PCE would have contacted all of these 3 nodes in order to instantiate the forwarding entry that they all require to act as an ingress, transit, or egress nodes. So let's go back to the root so we can see that. Let me copy paste this number. Oh, in fact, I'm going to copy paste this for simplicity. I'm going to go back to the root, hit the space bars a little bit. So here we go. So now I am in the root, and I'm going to ask for the information corresponding to a point-to-multipoint policy that is rooted on me, 1.1.1, that has the tree ID as shown. And here we can see the representation of the path that we saw earlier at the PCE. The portion corresponding to the root node is actually portrayed as operational data in the root node itself. So we can see the same ID, the color 10,000 that was used to compute the MDT, the fact that it has local LFA FRR enabled, my role, my incoming label, and my outgoing label. Outgoing label being the same. You can see here the fact that the outgoing interface is not displayed. Because this tree is being computed to provide local LFA, what the PCE will provide to the network element is actually the identity of the downstream node. And what this node will do then, it will actually look at the forwarding entry corresponding to that node, in this case 1.1.3, and it will use the primary interface used to reach that prefix. So in this case, to go to 1.1.3, my primary interface is gigi000. That's going to be my replication outgoing interface. And if something were to occur to this interface, I'm going to use my local LFA provided, computed by the IGP, going over gigi001 to protect against the failure of my primary interface, gigi0000. So this is the programming of the tree at the root So we're going to actually go on and go to a transit node. Transit node is here. It's actually router number 3. Let's actually take a quick logging at this node. In here, I'm looking at the same policy, same ID, same route. I'm a transit node. I have the same incoming label representing the entire tree, and I do have an outgoing interface where I'm going to be using the same label, and the egress interface is the interface that is going to router number 4, 1.1.1.4. Okay. So now we go, lastly, we go to the leaf. Let's quickly logging into it. Let me paste the value. I lost it. So here we are at the leaf. We're going to take a look at the same tree, and we can see that my role is leaf. I have no replication outgoing interfaces needed, and my incoming label on the tree will be the label of the tree seed, which is 15562. And this is actually an example of a multicast VPN that uses default MDT, where the MDT is represented by a point-to-multipoint SR policy that was computed by the PCE to minimize the IGP metric along the paths from the root to the leaves. Now, we're going to go back to the root. I'm going to close the demonstration by showing you a more sophisticated service. I mentioned that I would have a second multicast VPN. I'm going to call that VPN sample MVPN2. This other MVPN, in addition to having a default MDT of type segment routing point to multipoint, I will show you in a moment the color difference here is 10,001, but it also includes data MDTs. In the data MDT, we're also going to be using point to multipoint as our policies. We could instantiate up to 20 data MDTs, and we want to move traffic into data MDT immediately. These are all knobs to customize how soon you move data to data MDT, but the key part is the fact that both the default MDT and the data MDTs are allowed to be instantiated, and they're all both of segment routing point to multipoint types. Let's actually take a quick look at the color 10,001. As I mentioned, in the previous MDT for the other VPN, I was using metric IGP. In this case, my color 10,001 is actually going to optimize the path for the point-to-multipoint policy using the TE metric. You also have the choice to use the delay metric, which is the measured delay for the links in the network, as a optimization objective for a segment routing point-to-multipoint tree. All right, so let's now take a look at the segment routing database and the context information for the new MVPN that we are looking at now, the VPN number 2. Now we can see that I do have a default MDT. Default MDT has one egress PE or one IPMC leg, which is router number 4, and the tree seed is the ID of the next default MDT is different from the previous one, and it is 524290. This is going to correspond to another point-to-multipoint policy that this time, instead of being optimized for IGP metric, is optimized for the TE metric. And if we take a look at the new VPN that, if you recall, has data MDT allow, and we look at the cache of segment routing point-to-multipoint policies, we're going to see that there is a new tree ID 524291, different than the default MDT. 524291 is the ID of the data MDT that is being used to carry traffic for the multicast group 232001 coming from the source 3331, and this data MDT has one leaf that is interested on that traffic, and that is the egress PE 1.1.1.4. So this is an optimized tree that only includes PEs that are interested in a particular customer multicast flow. And with that, we end up our demonstration of segment routing point-to-multipoint policies. So as you have seen, in iOS XR 7.3.1, we introduced dynamic segment routing point-to-multipoint policies. If you were unaware, we already had shipping functionality for point-to-multipoint policies where the leaves and the routes were statically configured by the user. It's a very common use case, for example, in video distribution, where there is no dynamicity for the location of the PEs involved in a particular multicast delivery. So this is what we call static segment routing point-to-multipoint policies, already shipping before iOS XR 7.3.1. In conclusion, iOS XR 7.3.1 is another release packed with segment routing innovations that we hope you will leverage in your network. And we cannot wait to show you what we're cooking in our next release. Until then, keep on source routing. Thank you for watching. Woo! Okay, I'm gonna do it again.